Hi everyone. So welcome to our week 2 of our biochemistry reviews for the fall of 2020. So before we begin this week's content, I want to just very briefly go over what we talked about last week. So last week we started with chapter 1, which is just kind of the basics of bonding and the weak bonds, and moved into chapter 2, which was all about the acids, bases, buffers, Henderson-Hasselbalch, all that stuff. All right, and then we went about halfway through chapter 3 in our last review. Talking about delta G, and delta S, and delta H. Today we're going to build off of that, and then we're also going to hit chapter 5 about your amino acids, okay? So the first thing I want to do is review this from last week. So last week we said when you have a positive delta H and a positive delta S, your delta G is temperature dependent, and that means that it's spontaneous at high temperatures, okay? When you have a positive delta H and a negative delta S, your delta G is always positive, so you're never spontaneous. You never have a spontaneous reaction. And when you do that backwards, so a negative delta H and a positive delta S, you always have negative reaction, so it's always spontaneous. And when they're both negative, it's temperature dependent and spontaneous only at low temperatures. So we've been talking about delta G a lot, but there's a couple of different kinds of delta G, right? So the ones that are most commonly thrown around are delta G naught, delta G naught prime, delta G prime, all those things, okay? So it's really important to differentiate between them so that we don't get confused. So I'm just going to go one by one. Delta G is the Gibbs free energy, like full stop, okay? Delta G naught is the Gibbs free energy under standard conditions. So what does standard conditions mean? It means all concentrations are 1 molar. You're at about 298 Kelvin, so room temperature, and 1 atmosphere, okay? So that's great and all. And like I said earlier, delta G is the free energy at any point, so you'd be using Q instead of K. But delta G naught isn't perfect for every situation, all right? For example, in our biochemical systems, like our body, the pH is about neutral. So that's why delta G naught prime started getting used, because we wanted to make sure that we were discussing the standard state of biochemical systems, okay? So I want to just very briefly tell you guys converting between each of them. So like we said, when delta, I guess let me start off by saying this is the general form of the delta G naught to delta G conversion. You're going to say delta G naught of the reaction plus RT-ln-Q helps you convert to delta G, okay? When all reactions are 1, delta G equals delta G naught, like we discussed, all right? And like we said, that's standard state, biochemical systems, pH of 7 is used, so the natural log of hydrogen, or 10 to the negative 7th, is incorporated rather than just using a 1 for it. So there are 2 different forms of this, where H plus can be consumed or H plus can be produced, which are there and there. I'll just very briefly go over each. So when H plus is consumed, it's a part of our reactants, meaning it goes on the bottom or the denominator of our equation. So it's the natural log of everything over H plus. So what you end up getting by separating it out using the log rules, you get delta G naught prime equals delta G naught minus RT, natural log of 10 to the negative 7th. And in terms of equilibrium, is that they change your K prime is equal to 10 to the negative 7th times your K. And it's the exact opposite for when H plus is produced. So when H plus is a product, you get a your delta G naught prime. To convert to it, you get RT ln 10 to the negative 7th, whereas up here it was minus, here it's plus. And convert your K, instead of K prime equaling 10 to the negative 7th times KEQ, it's KEQ divided by 10 to the negative 7th. So I want to do a couple of examples of using these energy equations so that we can get into some good practice, okay? So the first question is, if a certain reaction has whatever delta H it has and whatever delta S it has, at what temperatures will it be exergonic, okay? So when I approach this question, I have to think of kind of 3 things. The first is, first of all, I have to find my mouse, there it is. The things that I've been given. So I have my delta H and I have my delta S, great. And I'm looking for exergonic. Okay, so this might be a new term to some of you guys. I'm not sure. What it means is, I'm sure you guys have heard of exothermic and endothermic. Those relate to delta H. Exergonic and endergonic relate to delta G. Okay? So, and feel free to type this in the chat because I do want you guys to answer these questions. If a reaction is exergonic, does that mean that its delta G is positive or negative? What do you guys think? Negative? Yeah, you're exactly right. Negative. Okay? So that means we are, still trying to find my mouse. There it is. We want a delta G less than 0. Okay, great. So how do we do that? Did not need to do that. Sorry, I need to scroll down just a little bit more. And let's zoom in a little. Okay. So what we're looking for here is getting a negative delta G, and we're dealing with delta H and delta S, so I know that the formula I'm going to use is delta S, okay? So one really important thing to keep in mind is the units of these things, okay? Delta H is almost always in kilojoules per mole. Delta S is almost always given in joules per mole, okay? Make sure that your units are consistent. All right, so I'm going to go ahead and convert this to kilojoules by saying 0.250. I apologize, 0. There we go. So let's go ahead and plug these in. So delta G equals 32 minus 0.25 T. Okay. So in order for the reaction to be exergonic, we need to know when G is less than 0. In order to do that, we need to know when G equals 0. So I'm going to go ahead and set delta G here equal to 0. Okay. So 0 equals 32 minus 0.25 T. We're going to add and solve, and we're going to end up getting that T equals 128. Okay, is everyone okay with that number? If you guys want me to go through the math, we can. Assuming we're good since no one's typed anything. So 128, what are the units of this thing? Anybody? Kelvin, perfect, yes. That's very important. Even though this looks like it should be in Celsius, it's in Kelvin, okay? So let's think about this, okay? At what point will let me rephrase that. Do I need to increase T or decrease T to make delta G a negative number? Okay, what do you guys think? Increase, you're exactly right. And we can prove that to ourselves by just saying, well, I know 200 is greater than 120. Let's plug 200 into here, all right? And if that one gives us a negative number, great. If it doesn't, let's try 100, okay? Just plug in a number that I personally choose these two because they're really easy, because 0.25 times 100 is just 25, times 200 is just 50. So in this case, we find that when T is greater than 128 Kelvin, delta G is exergonic, okay? So I want us to think about what that actually means, okay? If the temperature is greater than 128 Kelvin, well, room temperature is nearly 300 Kelvin, okay? So this is a really, really, really cold temperature, meaning this reaction is really, really, really exergonic, meaning it's really spontaneous, okay? So that's something to keep in mind, is just what do these actual values mean, all right? And the next question is based off of this exact same one. What will be the equilibrium constant, or K, of this reaction at 12 degrees Celsius, okay? So how do we do it? What do you guys think? No? Okay. All right, so we need a reaction, or I'm sorry, we need an equation that helps us go, hang on, someone said something. G equals, yes, you're exactly right. So we're going to use the reaction delta G equals negative RT ln F, and we're going to use this exact equation we used up there of delta G equals delta H minus T delta S. And we're going to set them equal to each other to solve for K. So important things are, I'm just going to work over from the left. There we are. Okay. So delta H is once again 32 minus, and this time we actually have a temperature, right? We have 12 degrees Celsius. Fortunately, it isn't good for us. So we're going to say 12 plus 273, because we need to convert to Kelvin, and then times 0.250. Okay, and that's our delta S. That equation is only used for standard condition. So you can use, it's a really good question. I believe you can use this equation at any point, because remembering that your entropy and your, your entropy can change depending on the temperature, and so can your delta H, I believe. And so they can move around a bit. But this is more to get you guys into the habit of combining these reactions, or combining these equations for our next question, okay? But that's a really good question, all right? And then negative R is our ideal gas constant. So the ideal gas constant is 8.314 joules, whatever else. The thing we care about is joules, okay? This is a problem because we set delta H kilojoules. We converted delta S into kilojoules, okay? So we need to convert this into kilojoules as well. So our real delta, our real R is 0.008314 in kilojoules, okay? Once again, we have our temperature of 12 plus 23, and we have equaling the natural log of K. All right, so we're going to solve this big ugly mess, okay? So the first thing we do is, obviously, we need to do 12 plus 273 to get that number. That's 285 times 0.25, okay? So on the left side, we have negative 39.25. Still can't find my mouse, there it is. Negative 39.25. That's going to equal negative 285 times 0.008314. Yeah, these problems are really tedious, if you guys couldn't tell. And I'm going to approximate this as 0.23 or 2.37, excuse me, 7 ln of K. We're going to divide them over, which 7, and then we're going to make E the base. I know that's the weird saying. Undo the natural log is, I guess, how I should say. Okay, and we get the K of this reaction to equal 1.5. K equals 1.5 times 10 to the 7th. Excuse me, that's positive 7. Okay, so again, let's think. What does this number mean? It means that this reaction is really, really, really spontaneous. Okay, it wants to happen, and it's going to happen a lot. All right. So that's that. Okay. The next question: what is a Van Hoff plot? Okay. So this one is based on the previous questions that we did, or rather based on the equation that we kind of came up with from the previous question. So if we have the equation delta H minus T delta S, and we set that equal to negative RT times the natural log of K, this is the relationship we use for the Van Hoff plot. We're just going to divide by negative RT from both sides. Okay? And then we're going to get the natural log of K is equal to delta H over negative RT plus T delta S over RT, and I took the negative and the subtraction and turned that into a plus. So then what happens here is these temperatures cancel, and so we get our final equation, or rather the final form of the equation that we get is over R times 1 over T plus delta S over R. So why is this helpful to us? If you're given a bunch of data, you can graph it, and you graph 1 over T versus natural log of K, and this is a y equals mx plus b plot. Okay, so this is y equals mx plus b. So we know that our y-intercept is going to be, intercept is going to be delta S over R. We know that our slope is going to be negative delta H over R, as long as we graph 1 over T versus the natural log of K, all right? So that's a really helpful way to just find them, because keeping in mind, R is a constant, right? We know what R is, and so it makes it a lot easier for us to basically just plug and chug and get these delta H and delta S values out of it, okay? Does anyone have any questions about Van Hoff plots, using them, anything like that? I'm sure that I actually answer them. If you guys do, feel free to type them in the chat at any time. I'm going to just move on to the next question since I don't think you do. Okay. When heat is absorbed during a reaction, the delta H of that reaction is, I'm actually going to go ahead and ask you guys this question. So I'm going to start a poll and let you guys answer it. What do you guys think? So we have two responses for positive, 3 for positive. Okay, I'm going to go ahead and end it there. You guys are exactly right. It's going to be positive. Okay, and the reason behind that, and this is something, to be honest, I miss a lot. That's kind of why I wanted to include this in here, just in case anyone else did. Is what's happening is the heat of our reactants. So this is reactants going to products. The heat of our reactants is going up. H is increasing, and that's why your delta H is positive, okay? And I know that, to me, it's really unintuitive. I don't really like that, but that's kind of the rationale behind it, okay? All right, so given the following reaction, answer the following questions. So this is a little bit confusing, so I want to just first, let's talk about what's happening. Well, obviously, the oxygen is getting phosphorylated, okay? So we're just going to have this big structure with an oxygen, and then with an alcohol group. That alcohol group is going to get phosphorylated and replaced with a phosphate group, okay? How does it do that? Because it uses ATP. This is its enzyme and cofactor. We're not really going to worry about these for an actual reaction, but what's happening here is plus ATP plus ADP, okay? That's a really important factor that is really easy to overlook, okay? Let's see some of the questions about this. Given this delta G naught value at this temperature, what would the delta G of this reaction be if all the concentrations were 0.5 mole? Okay. So, not a fun question, but we have the equation right up here. No, sorry, one more. Right up here for the conversion of delta G naught to delta G. Okay. Just to remind you guys, we're going to say delta G equals delta G naught plus RT natural log of Q. Okay. So coming back down to here, we're going to say delta G equals delta G naught plus RT natural log Q, okay? So we know that this is going to be negative 20 plus 0.008314 plus 50 times, or I'm sorry, 50 plus 273 is 323, because we need Kelvin, and then natural log of, well, hold on, this is going to be 0.5 times 0.5, there we go, over 0.5 times 0.5, right? So this whole thing is going to clean up to 1. What's the natural log of 1? No. Natural log of 1 is 0. So this entire term goes to 0. Ah, there we go. Thank you. In other words, the standard state that we use is 1 molar by convenience, but it could be any concentration, okay? So if all the concentrations are 0.5, same result. If all the concentrations are 0.2, same result, okay? And so in this case, delta G equals delta G naught, okay? Does that make sense to everyone? Does anyone have any questions about that? Okay. All right, number 6. If this reaction, oh, sorry. That makes sense. Okay, great. If this reaction weren't coupled to ATP hydrolysis, what would its delta G naught be? Okay, so this is an interesting question. So when we say it's coupled to ATP hydrolysis, what that means is this structure getting phosphorylated wants to happen, but to help it along, the ATP is breaking up one of its phosphates to convert itself to ADP, okay? Does anyone remember from your PowerPoint or your lecture how much energy that releases, the ATP hydrolysis? Ooh, jumping ahead. 50, not 50. The number that's most commonly thrown around is ATP to ADP is that delta G naught equals negative 31 kilojoules per mole, or it's like negative 30.5. Either are used. Yeah, exactly. I normally use 31 just because it's, you know, a whole number, but both are acceptable. So this reaction, what we're actually seeing is our big carbon structure, so carbon structure to carbon phosphorylase, PHOS, is going to have some delta G naught, plus delta G naught of ATP is going to equal our delta G naught that we got up here, okay? So putting that together, we see delta G naught of the reaction plus negative 31 equals negative 20, okay? So when we add those and subtract those, we get the delta G naught of the reaction will 11 kilojoules per mole. This is not spontaneous, right? And this is why ATP hydrolysis is used so often in our body, right? In units 3 and 4, you're going to be talking about glycolysis, you're going to be talking about the electron transport chain and cellular respiration. To create ATP, this is why ATP gives so much energy. And actually, I want to put that energy into perspective because up here, we found that negative 30-something kilojoules per mole gave us 1.5 times 10 to the negative, times 10 to the 7th as our K, okay? That's 15 million, okay? That's how spontaneous this reaction wants to be. In other words, ATP really wants to break up, and we want to use that breaking up to let our reactions work, okay? So that's a little bit about ATP that I think is really important, okay? And last question of the chapter, because I know this is not a particularly fun chapter with all these equations, okay? So in this chemical reaction, you have a delta H, a delta S, and a delta G naught in intracellular concentrations of ATP and ADP, and it's asking for the ratio of A to C, okay? So important things to keep in mind are, it's telling me intracellular, okay? Why is the intracellular concentration, why does that matter given this? Does anyone know? And that should be H+, I apologize. What do you guys think? No? Okay. So because we're inside a cell and we have H+, we're not just using delta G naught. We have to use the delta G, we have to use the delta G naught prime, okay? In other words, this big ugly mess, okay? So let's go back down. Okay, no, one more. Okay, so we need the delta G naught prime. Where's my mouse? There it is. Okay, delta G naught prime, and we said the delta G naught prime is equal to the delta G naught plus going back up, rather minus, or actually, hang on. H plus is being consumed, so it's going to be minus RT natural log of 10 to the negative 7. Okay. Right. Delta G naught minus RT ln 10 to the negative 7. Is everyone okay with why we're using this conversion factor? Rather, if you're not, please ask. Okay, so So we're going to go ahead and solve this, and we're going to say this is negative 3.5 minus 0.008314. 37 means 310, natural log 10 to the negative 7. Okay, so plugging all that in, we're going to get, and I like to take these in real time because I think it's a little bit more representative of how long ideally this might take, minus negative 41.5. Okay, so that's really plus 41.5. So the answer ends up being 38 about kilojoules per mole. There's our mouse there. So delta G naught prime equals 38 kilojoules per mole. Okay, awesome. So now we have our delta G naught prime. Are we done? I'm going to skip ahead. No, because we don't have the actual answer. We need the ratio of A to C. Okay, so let's go ahead and find that ratio. So we know that our delta G naught prime is equal to, slide over. Okay, there we go. There it is. Okay, delta G naught, which is kind of repeating that step, plus RT ln of Q. Okay, so we're going to go back and subtract our delta G to get back to that negative 41, or I'm sorry, positive 41.5 number. Should be positive. Yes, it should be positive. Equaling RT natural log of Q. And the reason that we have to do this backwards is because we need to figure out what Q equals, right? Because Q equals the concentration of C, and I apologize, I'm terrible at making these brackets, times the concentration of ADP, and I'm going to scroll over one, there we go, ADP over concentration of A times H plus times ATP. And I ran out of space. ATP. There we go. Okay. So we have to find Q in order to get to this. Okay. So we're going to divide once again 41.5 divided by 0.008314 divided by 310 Kelvin. And then we need to undo the natural log. And so we get 9.8 times 10 to the 6th. 9.84, give it an accurate number, times 10 to the 6th equals Q. Okay? So now what do we have? We know the intracellular concentration of H plus is 10 to the negative 7th. Great. 10 to the negative 7th. Okay? And we were told the concentrations of ATP and ADP are both 0.3 mole. And I'm actually going to go ahead and say 0.3 over 0.3 because that's these two, we can cancel them out. So what we're left with is really concentration of C over the concentration of A times 10 to the negative 7th. So if we multiply 10 to the negative 7th to the other side, we have this ratio that we're looking for, right? So I'm going to go ahead and do that. Excuse me. All right, so what we end up getting is 0.984 equals concentration of C over concentration of A. All right, great. So we're done, right? What do you guys think? All right, we're not done. And exactly, flipping. So this is another big process here. Make sure you know what you're solving for because these problems take a really long time. We don't have this, so we need to flip it. Once we flip it, we get, excuse me, we get 1.02. Okay, so what we're really looking for is A to C equals 1.02. Now we're done. Okay, so a couple of other things I want to highlight with this equation. I gave you these values. You didn't need them. a lot of times it's, you can be overwhelmed with these numbers, so I wanted to make sure that I showed like you don't always need these numbers, okay? All right, does anyone have any questions about this chapter before we move into chapter 4? Anything about energy? If it helps, I think chapter 4 is a lot more fun, okay? All right, I'm just gonna go ahead and jump in. If you guys have any questions, because I know you have to type them out, feel free to ask them at any time. So chapter 4 is about amino acids, okay? Amino acids are wonderful because they're all mostly the same. We have a question. Can you explain again your thought process in 7? Sure. So my thought process was, I know that because I'm in a cellular environment, I have to use our delta G naught prime instead of our delta G, instead of our delta G naught, right? So I went ahead and I said, let's convert delta G naught to delta G naught prime. Okay, that was our first step all the way through to, to right here. I'm sorry. I did not mean to do that. This is where we got delta G naught prime, okay? Then I had to think to myself, now that I have delta G naught prime, I need to figure out the ratio, I need to figure out Q effectively, okay? And this is the only equation that I have for it. And so I went ahead and I solved this equation, okay? And I told myself, okay, now that I have Q, what am I gonna do with it? Or, I'm sorry, I misspoke. Now that I have Q, I can expand Q out. Oh, no, do whatever I just did. Sorry guys, I am not the best with OneNote. Now that I have Q, I can highlight. Yes, that's what I'll do. So I need to use this to get to Q, okay? So once I have Q, it's as simple as this ratio right here to get to this, to get to the answer, okay? So I think it's really important to realize at the very beginning, well, what do I need, okay? In order to get the ratio of A to C, I need either a K or a Q, okay? Because we're dealing with an intracellular concentration, we're technically dealing with a Q. Because we're dealing with a Q, we need to convert to our new delta G, whatever it ends up being, in this case prime. And then, so we did it. Does that make sense? I tried to, okay, awesome. Sorry, I know it gets a little bit confusing sometimes. Okay, so amino acids. In my opinion, this is the fun part of this unit, okay? Amino acids, yes, you have to memorize them. No, it's not that fun, but once you've memorized them, they're all fairly similar and they're all fairly straightforward, okay? So, one of the things you do have to memorize is the pKa of the side chain, okay? Nobody likes this part, but there's a really cool acronym. Professors use it, some don't. I think it's really helpful. It's said out loud, it's St. Rocky Chad, or it's these letters, okay? And I'm not sure if you guys have seen it, so I'm just gonna go through it very briefly. What is the amino acid whose one letter code is S? Okay, that's where this comes from, basically, the one letter codes. Anyone? Serine, yes, excellent. Serine, all right, and I'm just gonna go ahead and go through the rest of these. T is threonine. R is arginine. Arginine, lysine. Y is tyrosine. C is, that's not there. Okay, cysteine. Is histidine. E is glutamic acid or glutamate, depending on whether you're in the acid form or the conjugate base form. And D is aspartic acid or aspartate. Aspartic acid. Okay. These are also the pHs in descending order. So serine and threonine, pKa of 13. I'm sorry, not pH. Arginine 12. Lysine and tyrosine are both about 10. Cysteine 8, histidine 6. Both of these guys are at about 4. Okay? So I believe these are all of the polar, or I'm sorry, the acidic and basic amino acids, or amino acid side chains. Let me be as thorough as I can. So this is a really cool acronym just to help you guys remember it. So in this acronym, I also want to make sure that I point out a couple of things. Serine and threonine are two of our alcohols, right? And alcohols, for example, has its kW of 14, right? Water or alcohol groups in general have pKa's ranging from like 10 to 16. So this number makes a lot of sense, okay? Arginine is a base, nitrogen 12, okay? Like all of these, try to make sense of them, okay? So applying this acronym or just having it memorized, what is the pKa of the side chain of cysteine, okay? What do you guys think? Go ahead and type it in the chat. I don't want to make a poll since this one's a bit easier. Anybody? It's on the screen. Okay. So it's 8. Oh, there we go. I think I just waited 1 second too little. Okay. All right. So now I have a couple of questions just about amino acid structure to make sure that you guys are, memorizing them. So which of these amino acids does not have an aromatic ring in their side chain? Okay. Does anyone know? Has anyone worked to memorize these yet? Because if not, we can go over them. Just see. Okay. I see hand raised. If you want to just go ahead and type in the chat, you can. You don't have to raise your hands. I don't mind it. Okay. So yes, C is correct. It is threonine. If I can ever find my mouse, there it is. Okay. Tryptophan is the one with the double rings. So let's see if I remember the side chains. And then I think this one's a nitrogen. It's something like that with those. Okay. Tyrosine is coming off of this is the central carbon. You have that. Then you have an aromatic ring and an alcohol, and phenylalanine is basically tyrosine without the OH. Okay, so just a quick reminder. All right, some general, information you need about these. What kind of bond is formed between two amino acids? Okay, and remember, see, yes, you're exactly right. It's a peptide bond. And on that same note, which is released during the formation of a peptide bond? Yes, water, you're exactly right. So very briefly, I'm just going to show it. So you have your central carbon with an alcohol and a hydrogen. You have your, I'm sorry, this is not your central carbon. This is your carboxylic group, and this is not a hydrogen. This is a C, and then you have your NH2 on this side, hydrogen, and then the R group. So this, you have your NH2 of a different amino acid, then your central carbon, COOH, variable R group, and hydrogen. So this hydrogen and this hydroxide both leave, and this nitrogen bonds with this carbon in an amide bond. Okay, so it's known as a peptide bond, but the specific structure that's formed, that's a carbon, my apologies, is an amide. Okay, that's something important to keep in mind. Okay, 12. For the following peptide, well, I think, is this? Oh no, yes, that's right. Okay, I have a different one of these. So for the following peptide, write the one-letter codes of the amino acids present in order. Okay. So actually, in this one, instead of just writing the one-letter codes, we're going to write the amino acids out, then write the one-letter code for this peptide. Okay. So what are some ways that are, in my opinion, easiest to do this? First, look for this. Okay. So this is that peptide bond with an amide. You've got the carbon, the nitrogen, the carboxyl group. This is what separates, I'm sorry, not carboxyl, carbonyl, excuse me. This is what separates two amino acids. So I know that to the left of this thing is my first amino acid. Well, that's the amine group, so I know that's there. That's the hydrogen, meaning this is my variable R group. Okay. Which amino acid has an R group that's just a methyl? Forming a peptide bond is a spontaneous reaction. In certain conditions, yes, especially when you're using the enzymes in your ribosome to help form it. But yes, it is pretty spontaneous. And yes, someone else said alanine. That's exactly right. Alanine is our first amino acid. Okay. Then I'm going to do the same thing over here. This is my next peptide bond. So I know that between these two is my amino acid. This is my variable R group, which means, I'm sorry, that's my hydrogen. So this is my variable R group. I know that the only two amino acids with sulfur are cysteine and methionine, and cysteine is the only one that's got a thiol, which is this SH. So this is cysteine. Okay, and finally, my very last one is to the right of this second peptide bond. I know that the COOH is my carboxylic acid group. Someone already beat me to it. Yes, it is glycine. You're exactly right. All right, so let's put these together and say alanine's one-letter code is, if I can ever find my mouse, there it is, A, cysteine's is C, and glycine is G. Okay. So alanine, cysteine, glycine, ACG, or this structure are all saying the exact same thing, okay? All right, next question. What happens to the C-terminus of a polypeptide and why? Okay, so this is an interesting question that your professors are going to expect you to know, particularly when you're doing some of your calculations for polypeptides. So does anyone have any ideas, or should I jump in? It gets deprotonated. Yes, but something a little bit more specific to the C-terminus. So your C-terminus, let me ask, what is its pKa? Maybe that's a little bit of an easier way to word this question. 4? Okay, yes. So this is the interesting thing. Someone said 2. You guys are both right, and that's kind of the weird, interesting thing that I want to make sure I address. Okay? The C-terminus of an amino acid, C-terminus of an amino acid has a different pH than the C-terminus of a polypeptide. Polypeptide, okay? And the reason behind that is, you can call it the inductive effect, you can call it conjugation, whatever it is you want to call it. The point is, by being attached to more and more things, it's getting more electron density from them, meaning that it's less acidic, okay? And so, which is which? Okay, this is where I'm going to turn it over to you guys. What do you guys think? Is 2 the amino acid, or is 2 the polypeptide? 2 is the amino acid, 4 is the polypeptide. Perfect. You guys are exactly right. And I lost my mouse again. Dang it. There it is. 2 and 4. Yes, perfect. Okay. This is really important to know when you're doing calculations, which is what we're actually about to start doing. Okay. So, what are the amino? So all of these questions, I think there's 4 of them, are going to be related to the enzyme or to the polypeptide YAK. Just 3 random letters. Okay. What are the amino acids inside this peptide, and what are their 3-letter codes? Again, a reminder: you need to have the 3-letter codes memorized. Actually, I think there's only 3 of these. Okay. So 3-letter code. So let's start with what are the amino acids? So Y is, there it is. Oh. Tyrosine, perfect. And so you already gave me the 3-letter code as well, which is excellent. TYR, okay. You're on. Sorry, what's the answer to 13? So the answer to 13, yes, let me go back to that, because we talked about it, we never really answered the question directly. The C-terminus of a polypeptide, pKa increases from 2 to 4. So the C-terminus of an amino acid has a pKa about 2. When it's in a polypeptide, so when you've got something that looks like this C-terminus is actually at about 4, okay? And the reason behind that is induction from the rest of the peptide, okay? That's the more direct answer to 13, okay? Does that make sense? Okay, great. So, all right, tyrosine. A, we said in this problem we just did, it's alanine. And its 3-letter code is ALA. And K, well, I don't know any amino acids who start with K. Uh-oh, what do you guys think? Yes, it's lysine. And the reason we can't use L for lysine is because it was already taken by leucine, okay? And that's LYS, perfect, okay? Are we okay with 3-letter codes, 1-letter codes, amino acids, like converting between those 3? Okay, terrific. All right, what is the isoelectric point of this polypeptide? Okay, and this is actually, these are the last 2 questions, so you guys see them. We want to make sure that we know how to do these. So what is an isoelectric point? Let me start there. Does anyone remember that word? It's pI, and specifically the pI is the pH exactly when the polypeptide's overall charge is neutral. Perfect, okay? So how do we do this? So I personally have a system that I like to use that I think is easy. So what I do is I list out the things I list out the entire polypeptide first. So what I do is I say N, T, A, L, and C. Okay, and this is the N-terminus and the C-terminus because those are really important. Then I say, does this contribute to pH? The N-terminus does, tyrosine does. I'm sorry, tyrosine should be Y, excuse me, and lysine should be K, yes. Tyrosine does, alanine does not, lysine does, and the C-terminus does. Terrific, okay, so I'm only looking at 4 pHs now. So now we need to identify the pKa's of each. So the N-terminus is about 9, tyrosine from our acronym is about 10, lysine is at about 12, and the C-terminus, in this case, since we're in a peptide, is about 4. Are we okay with that? Okay, terrific. All right, so now I go ahead and I draw 5 lines, or 4 lines, excuse me, 1 for each, 3 and 4, and I write them out in increasing order. So I say 4, that's a terrible 4 that looks exactly like a 9, 4, 9, 10, and 12, okay? So I want us to think of these as pH thresholds. When I'm below the pH of 4, what's my charge going to be? When I'm between 4 and 9, what's my charge going to be? 9 and 10, 10 and 12, and so on, okay? So below a pH of 4, our N-terminus is going to be protonated. So that's going to be, and I just put a positive sign, +1, okay? Our tyrosine is also going to be protonated. Do I put a positive here or not? 0. Perfect. So this is something that a lot of students get confused. You can either have an amino acid that switches between being negative and being neutral, or you can have an amino acid that switches between being neutral and being positive, okay? So even though tyrosine is protonated, it's going to be neutral, okay? All right, next, lysine. Lysine is going to be protonated since we're below, and it's also going to be positive, okay? And finally, C-terminus, protonated, neutral, okay? So in other words, my charge below a pH of 4 is +2. Does anyone have any questions about that? Okay, I'm going to assume you don't, but if you do, feel free to type them, okay? Between 4 and 9, well, N, Y, and K should all stay the same. I don't quite get it. Okay, sure. So we'll talk about it in a little bit more depth. So what we're looking at here is, will these things be protonated first? And then what is the charge if they are or aren't, depending on if they're not, okay? So below the pH of 4, I think you need to keep in mind the structure of each one. Yes, you absolutely do need to keep in mind the structure. So below a pH of 4, our entire thing will be protonated. And actually, I think it would be easier if we draw the polypeptide first. So if you guys want, we can go ahead and do 16 before 17, if that'll make it a little easier, okay? All right, yeah, sure. So let's do 16 first. So I'm going to do the N-terminus because I think that's the easiest. NH2, terrific, okay? Then I know that I have a central carbon, and I'm going to draw this as a line angle from like organic chemistry. If you guys want, I can also draw it later on as a like full structure with every carbon and hydrogen shown, okay? I know that this central carbon is going to have a hydrogen. I know that then it's going to connect to my carbonyl. So I know that there's a hydrogen here. And then I know that I need my variable, like my R chain, okay? So my first amino acid is tyrosine. What should its variable chain look like? I don't think you guys can type this out very well, so I'm going to go ahead and do it. It's a CH2, and then a benzene ring, and then an OH, okay? So this is one amino acid completely, right? Unfortunately, or not unfortunately, I should say, however, this part isn't going to be here because it's in a peptide, meaning that we need to form our peptide bond with an amide. Okay, so this is the, so this is the nitrogen of the following amino acid. Okay, the following amino acid, in our case, A, so alanine. And so this is the central carbon of it. This is going to, and I don't know why I drew one carbon. Yeah, I'll just draw that there. Okay, and this is going to the next carbonyl. So I know that every amino acid has its hydrogen. What is the R chain of alanine? Methyl, exactly right, CH3. So just that. Okay. So now between these two, I know again I have another peptide bond. Then I have my central carbon of this atom. Then I have my carbonyl, except this carbonyl, since we're at the end, is my C-terminus, so I can go ahead and draw the OH. Okay? Now lysine. Does anyone remember what lysine looks like? Or rather, at the very end of lysine is an NH2. How many carbons do I draw between my central carbon and my NH2? Maybe that's an easier question. 4, perfect, yes. Okay, so 1, 2, 3, 4, NH2. Okay, now I'm going to go back through and I'm going to highlight different things because I want to point out the certain things. So this is our N-terminus and our C-terminus. So these two are able to have a charge where the internal peptides are not, okay? And the reasoning behind that is this nitrogen is able to gain and lose hydrogen, I don't want to say fairly easily, but it's able to do so, right? It's got a pKa of 12, or I'm sorry, of 9. It's doable, okay? Whereas these internal amides, which I'm going to color in green, yeah. So this is the amide bond, okay? These internal amides don't like losing their hydrogen, so they are not acidic, not basic. We don't count them in our pH calculation, okay? Same goes for the carbonyls. The carboxylic acid has a pKa of 2/4. Internally, it doesn't have a hydroxyl group. It can't lose its hydrogen because it doesn't have one, okay? Finally, I'm going to draw our chains in blue. So depending on what your variable chain is, it may gain or lose protons, okay? So, okay, and there we go. So does this drawing make sense to everyone? Or do you guys want to go into a little bit more depth on anything? And we have plenty of time. I wanted to make sure to leave some time, okay? All right, fantastic. So now looking at this drawing, here are the things that we're looking at, okay? We want to ask what contributes to pH, okay? We know that our N-terminus does, okay? Because our N-terminus can gain and lose hydrogens with a pKa of about 9. That's why we drew, can I just, oh, I can highlight them in the same color. Yes, that's a good idea. That's why we drew this 9 right here, okay? We know that our C-terminus can gain and lose hydrogens with a pKa of 4. That's why we drew that there, okay? Our tyrosine, okay? What do you guys remember about alcohols from CHEM? Do they gain electrons or lose electrons easier? Lose. And I don't know how that table just came out. We're just gonna, there we go. They lose electrons. So it's gonna go from OH to O minus. All right, and now our next blue is alanine. Well, CH3 doesn't really gain or lose electrons easily at all, right? What about lysine? How does it gain and lose electrons? Does it gain or lose them? Lose. Oh, I'm sorry, no, not lose. Saw that in the chat. Gain, perfect, exactly right. An H3 plus, okay? So really what I'm asking you here is, well, when I say asking you, is what this question of isoelectric point wants you to do is ask, at a pH below 4, how many things will be positive, how many will be negative, how many will be neutral. Therefore, what is the overall charge? At a pH between 4 and 9, same questions. Between 9 and 10, same questions. 9 and 12, same questions. Above 12, same questions. Okay? And the reason that we do all of that is because we want to find out when it's neutral. Okay? So, and I'm going to go ahead and erase, and I'm just going to start this problem over again because I think that might be a better way to approach it. Okay? So, starting with a pH below 4, everything is going to be protonated, right? pH of 4, my N-terminus is going to be protonated, my tyrosine protonated, my lysine protonated, my carboxylic, my C-terminus protonated, okay? So now we have to ask ourselves, what is the charge of the protonated form of this thing, okay? Nitrogen, when it gets protonated in our N-terminus, is going to turn into NH3+. When pH is less than pKa, it's protonated, right? Yes, exactly right. Okay, so our N-terminus is going to have a positive charge. Okay, next, tyrosine. When tyrosine is protonated, is it positive, negative, or neutral? Neutral, that's exactly right. And I want to point it out right here. This is the protonated form, neutral. Okay, so that's why we put a 0 here for tyrosine. Right? The next one is lysine. When lysine is protonated, is it positive, negative, or neutral? Positive, perfect. Okay, and final question, our C-terminus, our carboxylic group, when it's protonated, is it positive, negative, or neutral? Neutral, perfect. So below a pH of 4, with everything protonated, we have our our polypeptide has 2 positive charges, so its overall charge is +2. Okay, does that make a little bit more sense? Okay, fantastic. So now between a pH of 4 and a pH of 9, okay? So this is something that you can get in the habit of doing, though it might be a little bit easier to go step by step at first, okay? So between 4 and 9, the only thing that changed is our C-terminus, right? Because we're still below the pKa of our N-terminus, we're still below the pKa of our tyrosine, and of our lysine, okay? So I'm going to go ahead and copy those 3 because N-terminus is still positive since we're below 9. Tyrosine is still neutral since we're below 10. Lysine is still positive because we're below 12. Okay? How did the carboxylic acid change? It lost its proton, so it took on a negative charge. Okay, I'm going to assume you guys knew that, but just didn't want to type it. So now the overall charge of our polypeptide is 2 positives and 1 negative, so it's only +1 between pH of 4 and pH of 9. Okay, does that make sense to everyone? Yes, okay, fantastic. All right, now between 9 and 10, I'm going to say the only thing that's changed is our N-terminus. Okay, so our tyrosine, we're still below 10. Our lysine, we're still below 12. Our carboxylic, our C-terminus, we're still above 4. So these are the same. Our N-terminus changed though. Is our N-terminus now positive, neutral, or negative? Neutral, perfect. Okay, so the overall charge of our polypeptide between 9 and 10 is 0. Okay, and this is what we're looking for. This is kind of like problem solved, we're done, but I want to keep going just to get us into a little bit more practice, just in case, okay? So between 10 and 12, I'm going to go ahead and say, once again, only one thing is changing, okay? We've only crossed the threshold for tyrosine, okay? So I'm going to copy everything else. Our N-terminus is still going to be 0 because it's deprotonated. Our lysine is still going to be positive because it's protonated. And our C-terminus is still going to be negative because it's deprotonated. What about tyrosine? It just got deprotonated. Is its charge going to be positive, neutral, or negative? Anyone? Negative. Perfect. All right, that's exactly right. Okay. All right. Negative, meaning that our overall polypeptide charge is -1 by adding them together. Finally, at 12, and I'm going to kind of go ahead and jump through this. Our N-terminus did not change. Our tyrosine still negative. Our lysine lost its positive charge, making it neutral, and our C-terminus didn't change. So we have a -2. Okay. So this is about the pattern we normally see with isoelectric point. +2, +1, 0, -1, -2. Okay. There are exceptions. And I know that everyone hates that, but it's really important to know that there are exceptions. If I gave you an amino acid, or I'm sorry, if I gave you a polypeptide that was YYK instead of YAK, how would this, or I don't want to say how would this pattern change, because I think that's a little bit of a weird question. But what we would see at 10, when tyrosine changes its charge, 2 tyrosines would change in charge. They would both be deprotonated, and so it would jump, okay? So it's really important to, yes, understand that this pattern is generally going to be what we see, but not to just assume that that's what we'll see because it happened this time, okay? If you have 2 amino acids in your polypeptide at the same pH or about the same pH, like glutamic acid and aspartic acid, like serine and threonine, like 2 of the same amino acid, you can have a jump of 2 in between a pH threshold, okay? So coming back to this question, I just wanted to say that before we got a little distracted. Coming back to this question, our isoelectric point is between 9 and 10, okay? We don't know the exact point, so what we end up doing is we average them, and I am going to probably draw. Then what's with that jump? What do you mean? I'm sorry, I'm not sure I understood the question. YYK? Sure, so with YYK, and I'm going to just very briefly do this one since I know that we're running out of time. We only have about 10 minutes and I want to save time for your questions. Let's see, we'll do below 4, below 9, and at 10. So below 4, you're going to have positive terminus, neutral, neutral for both your tyrosines and positives. You're going to have +2. Over here, the only thing that's going to change is your C-terminus, which is going to be 0. I have to draw that one. So you're going to have +1 from positive, 0, 0, positive, negative. And then over here, between 9 and 10, you're still going to go to 0. But then once you cross 10, I'm sorry, you're going to go positive, negative, negative, positive, negative, because both tyrosines are going to be deprotonated. And so you're actually going to jump to -2, okay? And the reason for that is because both tyrosines are going to be deprotonated at the same time. And so when that happens, your pH is going to change by 2 rather than 1, okay? Does that make sense? Is that going to affect the PI? In this case, no, but it can, okay? And that's why I want to make sure that we don't just get in the habit of saying +2, +1, 0, -1, -2, because that's not always the case, okay? I know it's really like aesthetically pleasing and I love it when it happens that way, but it's not always going to happen and it can jump. And for example, if, let me think of a good example. So if we had, for example, let me make sure this works. Okay, yes, it should. Y, Y, K, and E, so glutamic acid, then, sorry, I need a little bit more space to do this. Give me one moment. Okay, so Y, Y, K, and E. So we're going to have at 4, or I should say below a pH of 4, your N-terminus is going to be protonated. Your 2 tyrosines are going to be neutral. Your lysine is going to be positive, and your glutamic acid is going to be neutral, be protonated, and so will your C-terminus. So you'll have an overall +2. Once you get above 4, your glutamic acid and your C-terminus will both get deprotonated. So you'll get 2 negatives, and your pi will be right there. And I'm assuming this will be 9 still. Does that make sense? So in that case, your pi would change. Okay, so just keep in mind it's not always going to be, -3, -2, -1, 0, +1, +2, +3. Okay. Right. So finishing this question, the isoelectric point is somewhere between 9 and 10. We don't know the exact point, so we say 9 + 10 over 2, and we average them to get a 9.5. Okay. So the pi of our polypeptide is 9.5. Does that make sense? Okay. And I'm going to go ahead and actually, this is the end of the actual review. If you guys have questions, feel free to ask them. I think I'm going to go ahead and stop recording it now, though, okay?